This semester for our mechatronics project for FAMU FSU College Engineering, I decided to do a KT88, a single-ended amplifier control system in terms of volume control and a safety system for a Class A amplifier. For this system, starting off, you have to understand the background of a vacuum tube amplifier. How vacuum tube amplifiers work is the main goal and objective of this is to amplify inputted sounds from either a receiver, an iPhone, or a vinyl player. The way that it works is you have a power system that gives 120 volts from the wall and upscales it to 450 per channel. This goes to channels where your signal goes through. You have a vacuum tube. Inside the vacuum tube, you have a cathode and an anode. The cathode is a metal, the filament in it. Whenever this adds heat to it, it gives energy to that metal. That metal then heats up and electrons separate from the neutrons, creating valence-free electrons. When that happens, your anode is positively charged and your cathode is negatively charged. Inside typical air, it's hard for these electrons to travel. However, in a vacuum, it's easier for them to travel, and so they move from the cathode to the anode in that vacuum. Inside of that, you have a grid or a bias. By changing that grid, it's in between the cathode and the anode. If I put the signal inside of that, it amplifies that sound. So the way that this system works is you have your power supply of the 450 volts that comes through here. It goes from AC to DC so that it can make sure that you only have positive power going to your tubes. It goes through here. These are two stages of amplification. The first stage of amplification, and then the second one, this has a gain around 7, this has a gain around 17. From this is where you're having your signal coming into your grid to be amplified. Whenever your system comes in through here, it is amplified, goes out to your power transformers, which then takes your high voltage and makes it into a current. This then goes to your speakers, to either side of your speakers, to play your song, to amplify it from a small iPhone to a lot bigger system. So for the actual mechatronics side of this project, this amplifier itself does not change volume, and I wanted to change volume or gain, and the way that you do that is you put an attenuator in the middle of that, and in between the input and output signal. This changes the resistance to change the volume, but to do that, what it takes, so this isn't the attenuator itself here. So if you look in, this is what's changing in the input signal. Comes in here, goes to the attenuator, and this is what changes the volume of the system. However, to avoid having to do this manually, I put in a system with an Ardunio board, the 2560 Mega board, that allows to take in an IR receiver that if I press a positive charge or give a positive signal to it, it is able to upstep the motor without having to do it with my hand, without having to do it manually. This allows the system to go up or down. It has a time delay on it to make sure that it steps the appropriate amount. So as I turn it up, you can hear the volume of the song getting louder and louder. This allows me to do it with free-handed without having to grab it myself. The power going to this stepper motor is 12 volts. It's rated for 12 volts and it has about 1 amp going through it. I use a standard power system for that to supply my power. So when that comes in, my signal comes in my IR receiver. It tells the stepper motor to go clockwise by 30 degrees. The attenuator steps up. That's 2 steps with the attenuator, and also 30 degrees. This allows your volume to increase, and then whenever I want to go downwards, I press a negative charge, and that gives it to go counterclockwise in the opposite direction by also 30 degrees. This allows it to go up and down in the volume that what you want for your system. So that is one side of the system, and the second side of the system is safety concerns. When you're dealing with this, you're dealing with extremely high voltages, and at points it can actually get extremely dangerous. If you're not careful, you don't know what you are doing. If you were to grab 450 volts, it could damage you, and if you were to grab it with both hands, it could potentially kill you. So to avoid kind of having these situations, I wanted to take as much safety precautions as possible. In doing this, you want to add different systems like adding in a fuse. I added a fuse into the back of my amplifiers. In the case of an emergency, it would bust that fuse, but I wanted to add an extra step. Adding this extra step is the second phase of this mechatronics project. What it does is, so I have current going through each of these KT88s, these tubes. I have 80 milliamps going through each, but they both seeing 450 volts and about seeing 5 volts to the filaments. So what I wanted to monitor is I wanted to monitor the current going through these, and so I have a voltage divider on the bottom side of it that is actually splitting it and putting it in parallel to monitor how much current is going through it so I can see. And so what this does is I put attenuators on there, so instead the voltage divider has exactly 3 volts towards it. So I can see that, okay, if 3 volts, there's 6 milliamps going through this. So I can do conversions to figure out how much is going through it to see what is actually running through my amplifier or my KT88. So if you look here in the LCD screen, what I did is I put in here is the different left channel, right channel currents in terms of milliamps going through each of the KT88s. This is at 80, so which is exactly what I'm seeing. This is iterating every second to know that it's constantly checking my system. So this is going into my mega board and telling me, okay, you have 80 milliamps going through this. This is what I want. So in the case of a power surge or a power shortage, this number is going to change. This would be like a lightning strike, a busted bulb. In this case, it might not always bust the fuse, but I want to prepare for it if it doesn't. So the way that I do this is whenever this drops between a certain limit, if it goes above 90 amps or if it goes below 75 milliamps, it shuts off my system. It says you have a power surge or you have a lack of power, and it sends a message to my relays, and my relays then close the circuit to the thing, or it opens the circuit to close it off. I'm using a normally closed relay to this board so that it can shut it off. Now with this system, as you can see, is as I increase, so the way to basically show and demonstrate a power surge or power source, I'm using a variac, which varies the AC current or the AC power coming from the wall. Our wall voltage here is around 110. This amplifier needs to see 120, so I can upscale it to 120. But to show you how this system works in terms of reading the current drop, I can change using the variac the voltage going up to 130 or down to 110 to see how the current is. So doing this is my variac. So whenever I change this is in terms of changing percentages. And if you look on the LCD screen here, as you can see, as I change my current, as this drops. When this drops, it says power or power low turn off. This then tells my thing to then open up my switch to turn off my amplifier. Now, if I go in the other direction, so I'm going to take this back up to 80. So this is now going back to an on system. So if I overpower my system and if I go up to around 130 volts or 140 volts, it's going to see this and it's going to say too high the power, turn off my system. And I'm going to have a signal light that's an emergency for this system. So the way that a challenging part with this project is that whenever you're using vacuum tube amplifiers, you never want them to immediately turn on or off. You want them time to have to heat up because you're adding energy into the filament, so you want them to kind of to heat up over time. So that being said, you have to add a delay into your system. So for my system, I have a 90-second delay, meaning whenever I turn on both of my systems, it waits 90 seconds before starting to read my milliamps. The reason why I'm doing this is because if it was to read before that, as this is heating up, even though it is seeing that 120 volts, it's going from 0 to 20 milliamps to 30 to 40, and then it ramps up to 80 milliamps. In that time, if this sees, oh, it's less than 75, it would shut it off and it would never allow me to turn on my amplifier. So by waiting 90 seconds, it gives me that time to get up to my full 80 milliamps, and then from there start monitoring and then shut off my amplifier. So kind of the full scope of why we were doing this project and why I decided to do this was to kind of dive into the finer things in terms of audio and understanding how amplifiers work and understanding what's dangerous about it and also what gives it such high quality in terms of a Class A amplifier. In doing this, I wanted to kind of push forward and go into the actual control systems in terms of how do you change volume and also how do you maintain safety at all points in times. Last thing I'd like to say is I'd like to say thank you to Blueglow Electronics for giving me the schematics to help me build this KT88 amplifier, and also to John Chapman for giving me some of the systems for the motor and for the attenuator.